When we look at the history of the atomic model and our understanding of the behavior of electrons and their energies, then we really have to focus on the hydrogen atom, because a hydrogen atom is made up of one proton and one electron. And so it's really the simplest system that we can look at as chemists to really understand the behavior and the energy of electrons. So I want to talk a little bit about Niels Bohr and kind of his ideas about an atom. I do have a video that's just focused on the Bohr model of the atom, so it's good to review that kind of coming into this one if you haven't had a chance to look at that yet. But the summary of that is that Niels Bohr, who's a Danish scientist, said electrons exist in energy levels, in these kind of shells, is the way that he conceptualized them. And an atom looks a little bit like a bullseye then, with a nucleus at the center and these energy levels radiating out that have electrons with specific energies in them. And the energies are quantized, which means they come in discrete packets. So those energies can only be certain shells. You can be an electron in shell 1 or an electron in shell 2, but nowhere in between. And the way we see this quantization is in kind of these whole number n values that are called our principal quantum numbers, which refer to the individual shells. So again, if we're kind of thinking about our model of the atom here, here's n equals 1, n equals 2 as we're kind of radiating out here. So the further away we get from the nucleus, the greater the potential energy, and these n's are all greater than 0 whole numbers. And the energy can be defined by what is called the Rydberg constant, which is 2.179 times 10 to the negative 18th joules divided by that n squared. And so we can use this information to build kind of an energy level diagram, essentially, for our hydrogen. So if we picture our nucleus down here at the bottom, as we move away from the nucleus, we get greater energies. So if we're thinking about our n equals 1 here, that's going to be n equals 1, this kind of sphere, this shell, then the Rydberg constant is going to be negative Rydberg constant over 1 squared. So it's just going to be our negative r sub h. So negative 2.179 times 10 to the negative 18th joules. Now when we go to 2, there's kind of a big hop up here, and this would be, you know, the negative Rydberg constant over 2 squared, which would be 4. For 3, it'd be negative Rydberg constant over 9, which is 3 squared, negative Rydberg constant over 16, over 25, kind of etc. up. Now you'll note as we get closer and closer together then, kind of as we increase our n, as we move away from the nucleus, that electrons in these upper energy levels are going to get closer and closer and closer and closer together. And as n reaches infinity, so as I'm moving further and further away from the nucleus, ultimately I'm going to lose that electron, right? But if I was reaching towards infinity with my distance from the nucleus in terms of my energies, then that's going to give me a value that's negative r sub h, my Rydberg constant, over something gigantic, and that's going to give you 0. Right, so I'm reaching towards 0, which sounds a little bit weird, but once I hit 0, then I've lost the electron, right? The electron is gone, it's no longer on the atom. If, again, we're visualizing our nucleus here at the bottom. So we're thinking about a hydrogen atom. We have this one electron. It can be in any of these different energy levels, right? And the electron would have to absorb energy in order to get to these higher levels. It would emit energy if it goes to the lower levels. And that's kind of what he says here in his second postulate, that any electron can move from these different energy levels from one to another, but not in between. So it exists in 1, it exists in 2, nowhere in between. It's not transferring in between. And this is called a transition. So I'm transitioning from n equals 1 to n equals 3, for example. And that can be described by a change in energy. There's an energy that's associated with each of those energy levels, which we just saw as our negative Rydberg constant over n squared. And so if we wanted to solve for that, then we'd end up with a delta E, which is final minus initial. And we know that our E initial is going to be wherever we started, this shell, and our negative Rydberg constant, and our final, this is going to be where we ended. And so if we kind of plug and chug these in, and I do some rearrangement, we end up with the delta E is equal to the negative Rydberg constant times 1 over the final principal quantum number squared minus 1 over the initial principal quantum number squared. And make sure that you believe my algebra here. Make sure that you rearrange and can solve for yourself. But we can use this equation then to solve for these different transitions, these hopping around with our electrons to these different energy levels. So let's say we wanted to calculate the delta E from n equals 2 to n equals 1. So for visualizing this, we have our kind of n equals 2, here's our n equals 1. So our electron is going to go from the second shell down to the first, and some energy is going to be emitted in the process. Okay, so that's what we're calculating, is what is that delta E? What is that change in energy? How am I going to see this? So the delta E here is equal to my negative Rydberg constant, 2.179 times 10 to the negative 18th joules. And then I'm going from this to this, right? So here's my initial. If relating back to my equation up here, here's my initial value. I started at 2. I'm relaxing down to 1. So that's my final principal quantum number. And when I plug and chug here, I end up with a delta E that is equal to negative 1.634 times 10 to the negative 18th. And again, my units are in joules because I have n's here that are whole numbers with no units associated with them. They're unitless. And my Rydberg constant is in joules. So that makes sense for a delta E. We would expect our energy to be in joules or kilojoules or some variation on a theme there. And it makes sense that it's negative as well, because the negative energy by convention means that the energy is being released from the system out into the surroundings. So the electron was higher energy, it's now a lower energy. Where did that energy go? Well, it had to be released, and it was released by this much. Now that's all well and good. Maybe we don't have our heads around what energy actually is and how it relates to the light that comes out. And since the energy is actually emitted, we can determine the wavelength of the light that comes out. So Einstein says that we can relate the energy to the frequency. So h here, of course, is Planck's constant. And our nu there is our frequency. And of course, E for energy. So if we take what we just saw from our Niels Bohr postulates there, that the negative Rydberg constant is equal to 1 over the principal quantum number for the final state minus the initial state, then we could say if that's equal to delta E and the energy is being released, then I can think about that as a negative. It's going to make this guy a positive, and that's all going to be equal to my h nu. So this amount of energy that I'm releasing is going to give me certain frequency of light coming out. Now remember that our speed of light and our wavelength and our frequency are all related by this equation. So if I rearrange to solve for the frequency, then that's going to be equal to the speed of light over the wavelength. So now I can say, well, let me plug this in for my frequency. That gives me kind of h times my c over my wavelength, which gives me my Rydberg constant, which is now positive because we're talking about a release of energy. And then this is times my final state minus my initial state. And now if I do some kind of clever rearrangement here, we have this guy's a constant, this one's a constant, this one's a constant. So if I do some rearrangements to put all of my constants together, then I end up with 1 over my wavelength is equal to the Rydberg constant over hc, Planck's constant times the speed of light, recall. And then now we have this guy with our final principal energy level minus our initial. And again, we're just doing this derivation to kind of relate this whole goal of all this is to relate the wavelength to this transition. So what wavelength of light are we going to see when we transition from these different energy levels? And now when you plug all of these in, this gives you 1.097 times 10 to the 7th, and this is per meters. So kind of meter to the negative 1, or you could think about it as a per meter, however you want to think about it, 1 over meters. So we have this reaction, this equation then, that's now going to give us a relationship between my wavelength and this transition. So let's calculate, for example, if I wanted to look at kind of an electron that's going from n equals 3 to n equals 1. So I'm starting at the third energy level and I'm going down. So again, if we're kind of visualizing this here, then I have an electron that's up here and it is relaxing down to here. And in doing so is going to release a certain amount of energy. And that energy is going to have a specific wavelength. So then we'd say, well, what wavelength is it? Well, we'd use that equation that we just came up with. So this is kind of 1 over the wavelength. Our lambda is equal to this combination of constants. So this is including my Rydberg constant, it's including my speed of light, it's including Planck's constant. And then we're going to transition from the, here's my final, minus where I started, my initial. So I'm going from 3 to 1. And when I plug and chug here, I end up with a wavelength equal to 1.025 times 10 to the negative 7th meters. Now you'll note that I ended up with meters here because my constants, when I combined all their units together, gave me an answer in per meters. And then I took the inverse over here. So when I take the inverse of this, that's just going to pop it back to the top and give me meters. And so I end up with, maybe it's easier to think about in terms of nanometers. We talked about that with the electromagnetic spectrum, that 1 meter is equal to 10 to the 9th nanometers. So that would give me, and then, you know, if I round to 3 sig figs, or if I don't, it doesn't really matter, 102.5 nanometers. So now this is my wavelength. This is the wavelength of light that is coming out. Is this in the visible range? Would be kind of an interesting question. And no, we'd see that that's not in the visible range compared to what we know. We know that the visible range is between 300 and 700-ish kind of nanometers. So this falls outside of that range. It's shorter, so it's probably somewhere in kind of the UV kind of range, higher energy. So if we're looking at these transitions then, if I'm going down, right, from higher energy to lower energy, energy is being emitted. If I'm going up, right, if I'm going from a lower energy level to a higher energy level, I have to put energy in order to make that happen. So I'd have to put in specific wavelengths to go the opposite direction. I can get specific wavelengths out going down. Now again, this is only good for hydrogen, which is always frustrating for students, but really it gets so much more, infinitely more complicated when we go beyond 1 electron. As soon as we get outside of a 1 electron system, things get very complicated very quickly. And for hydrogen and hydrogen's atomic spectrum, there's an equation that we use because we are interested in visible light. So let's think about the atomic spectrum. And in order to talk about the atomic spectrum for hydrogen, we have to talk about a guy named J.J. Balmer. And what is called the Balmer series. So what J.J. Balmer did is he said, well, I'm going to use this equation that we get that relates all of these constants together, and then we're going to think about the visible light that comes off of the hydrogen atom when it burns, right? Because the visible light is what we as humans are interested in because that's what we can see. So this is the rainbow spectrum that we can see of visible light. And he said, well, I can figure out all of the visible light by plugging in my values that go down to the second energy level. So if I'm thinking about just this guy, this one's really important for visible light. So if I take my 1 over my wavelength times is equal to my constant here times meters to the negative 1. And my final here is now always the second principal quantum number. It's always that second energy level. And this is going to be wherever I started from. Then this is going to spit out all of the visible wavelengths for hydrogen. And so I can go from 3, I can go from 4, I can go from 7. All of these are going to give me visible light. So that's kind of an interesting feature from this, and is why the Balmer series is so important.